y bar, because for a single individual, if you don't know anything, your best guess for x is x bar, and your best guess for y is y bar. So we start there at that point, and then we look at changes in x affecting changes in y from there. So conceptually, we know that line is going to be there because what we're doing when we make a regression equation is trying to describe the relationship between these variables so that we can predict people's values. So your starting point is going to be your best guess. That would be right here. Mathematically, how do we know? You don't even have to trust the conceptual stuff. You can go right to the math and show yourself that it's going to be there. Like this. If our sum of squared errors line is going to approximate that y equals mx plus b. This is just algebra. That's the line of, or that's the equation for a straight line. The intercept and the slope, and then you plug in all your values of x and y, and that will give you a straight line. So if you had a point, whatever the slope is, if our slope of the line is 2, right, and you've got the point 1, 1. We'll create our table here. 1, 1. You put a 1 here, you're going to get 2. And if this is 1, you have 1 equals 2 plus b. So b must be -1, right? There. That's our equation. If you have the point, let's see, what else is on this line? 2. We've got 2 times 2 is 4. And if this is -1, well, actually, we don't have the time to do this, actually. The equation for a straight line is y equals mx plus b. If everybody's cool on that, yeah, we've done that one into the ground, right? So our sum of squared errors line is going to be, for every point we have, I need the white one. You can see this white chalk one well. Sort of. For every point, we've got all the points that might be on our line. You've got x1, y1. You've got x2, y2. You've got x3, y3, all the way up to xn, yn. This is every point that's going to be on our line, all the way up to the number of points we have. That's what the n is. So if the equation is y equals mx plus b, and our sum of squared errors is going to try to get us whatever our line is. These are our predicted values of y. If we've got actual values of y like this, or some of them fall on the line, some of them not so much. We got a few really weird outliers, whatever they are. And this is our best fit line. We want to position this line so that these distances added up, the squared different distances, right? Because we don't want to cancel out the positive and negative. We've talked about that before. We want to position this line so that these lengths, all summed up together, are as small as they can possibly be. If our line went like this, instead to try to depict it, we'd have different distances for these dots. That one would be right on the line now. That one's right on the line. But this one's now further away. This one's now further away. This one's closer. This one's now further away. This one's now right on the line. This one's now further away. Both of those seem like they're getting fairly close to the dots. We want the one that makes, if you add up all of these lengths from the line, which line that you could possibly draw is going to give us a sum of squared errors that is as close as possible to 0. How do we calculate what it's going to be? Well, if you're going to take the distance from each one to the line, then the sum of squared errors line is going to be y1, so the value of the actual value of y, minus mx1 plus b squared. So that we can get the first error distance. Actual value of y, so if predicted value of y is mx plus b, y equals mx plus b, then you've got m times 1x plus b, and you subtract that, because that is your predicted value of y, subtract that from y1, the actual distance, and then square. Right, sum of squared errors, that's what we're computing here. Right. And then we do that for the next dot, y2 minus m times x2 plus b squared. To get each of our sum distances. You do that all the way up to yn minus m times xn plus b squared. That's going to give us our sum of squared errors line. We want our line to have the right values of m and b such that this summation is as close as we can get it to 0. Right? That's what we're trying to do here. If you write each of these out, you can kind of expand them so we can see what the equation is that we're working with here. The other side of my board not as pale? Yes, it's not. All right, so let's do that. There we go. Thing just needs a good cleaning, huh? Can you guys see this? Yes. Kind of can. Let's see what you see. How do I see just me? Okay. You guys can see this space right here? Yeah, okay. If you look at each of those, you've got y1 squared plus, plus 2y1 mx1 plus b plus mx1 plus b squared. what I'm doing is I'm just expanding out that equation. So you had y1 minus mx plus b squared. That becomes y1 squared plus 2y1 times mx plus b squared. Right? You can expand them even more. So you would do this for for y1, you do it for y2, y3, y4, all the way up to yn. You can expand them out even more so that you've got y1 squared minus 2y1 mx1 minus 2y1b plus m squared x1 squared plus 2mx1 plus 2mx1 m squared x squared 2mx1 b plus b squared. This is just this expanded. It's the same thing. Okay. So like this over here, this mx plus b. You guys remember how to do this? It would be mx times mx. That gives us that 2mx. The outside, then you do the inside. So b times mx right there. And then the outer edges, x times b. Mx times b. That gives us the 2. And then the ends. So b times b, and that gives us b squared. Like this is just an expansion of this. So this equation and this equation are the same thing. You would do that all the way for each of them up to yn. Right? Expand them all out more. If you do all of that, if you plugged it in for every single point, then this equation would end up being, right, so all the way up to y sub n. You end up with this super long equation that looks like this. Y sub 1 squared plus y sub 2 squared plus all the way up to y sub n squared minus, we can take out the m here. So you got 2y sub 1 times m x sub 1. You can make that 2m times x sub 1 y sub 1 plus x sub 2 y sub 2 all the way up to x sub n y sub n. So this is this, this is this, and then this one becomes negative 2b, this here, 2b. So we're taking out the things that are constants for us. 2b times y sub 1 plus y sub 2 all the way up to y sub n plus m squared, this part, times x sub 1 plus x sub 2 plus all the way up to x sub n plus, now we're over here, 2mb. Right, so this one, this one, this one, leaving just our x sub 1s, right? We did the m squared, 2mb times x sub 1 plus x sub 2 all the way up to x sub n plus n times b squared. That's this part here. You just multiply that by n. So now in our simplifying, it looks like our simplified equation has become quite this long, big mess, doesn't it? It's a whole bunch of crap now, where it was nice little orderly little equation. But this is what you would do. This is how the whole thing walks out, basically. You can solve the whole thing to simplify each of these sections, because you're just adding up all of the sums. You would get y sub 1 plus y sub 2 plus all the way up to y sub n, all those squares that you're getting. If you add all of those up and then divide by n, then you're going to get the mean of y squared. So all of this mess. You can simplify that out and just plug in y squared, mean of y squared for each of those. Or take this equation, this whole part that we have multiple times. There, right there, right there. You have it for x right there, right there, right there. It's also equal. You can take this whole part. Instead of dividing it by n, you could say that this whole thing is equal to n times the mean of y squared. Right? That's much simpler. Right, but I'm walking through how we got to here. You can do the same thing for x. You can do the same thing for each of these. X sub 1 times y sub 1 plus x sub 2 plus times y sub 2 plus x sub n times y sub n, all of those. You could just write 2m mean of x times y. It's a simplified way to write that whole big thing. You will end up and seeing some of the squares. Some of you are quite literally falling asleep. Bless your hearts. Hang in with me here. I know that this seems like a great big mess, but this is going to show you why this makes sense. And I want you guys to get this, because I don't just want you to be able to do statistics in a stat program or trust that this is a thing. I don't want you buying it because a statistician told you, trust me, it exists. You guys have all of the knowledge to know why it exists. And I want you to keep that. If you do that all the way down, you simplify those out, you end up with the sum of squared errors line is going to be n. So all of each of these for sub 1, sub 2, sub 3, for every single point on your line. N times the mean of y squared minus 2mn times the mean of x times y minus 2bn times the mean of y plus m squared times n times the mean of x squared plus 2mn. Oh, I lost my place. M squared n 2mn xy 2bny m squared n x squared 2mbn times the mean of x plus n times b squared. All we did to get here was take the equation where you get the sum of squared errors for every point or solving the equation for the first point of x, the second point of x, the third point of x, the fourth point of x, to get the distance between the actual y and the predicted y. We've simplified all of that to say, okay, here it is. N, however many points you have, times the mean of y squared minus 2mn times the mean of x times y, minus 2bny, or times the mean of y, plus m squared n times the mean of x squared, plus 2mbn times the mean of x, plus nb squared. We're looking, and I know this is still a whole bunch of letters and numbers, right? But each of these y's and each of these x's, they stand in for real numbers that we know, right? We want to optimize this equation, because what we're getting here is the sum of squared errors. We want to optimize this to find the values of m and of b that get this as close as possible to 0. So we're trying to get this value as close as possible to 0. And we could plug in all of the different options until we get the values of b and of m that make this equation as close as possible to 0. We have x and y for every single point, because we're basing our equation we're making on real data. So every xy, x1, y1, x2, y2, those are real numbers. We could plug them in and solve it out. The only thing that we're missing on each of these is the b and the m. We have to solve for those. We want the m and the b that's going to make the sum of squared errors as close as possible to 0. So if you set this equation equal to 0 and solve for m and for b, respectively, that's what we're going to do to get our values of m and b. So if you treat all of those other things as constants, then you just look at the things that are relevant for m and for b. So for the m equation, you're going to say 0 equals, we don't care about this because there's no m in there, so just forget that for now. It's going to be 2n mean of xy. Right. We're taking out the m's. Plus 2n mean of x squared m plus 2bn mean of x. If we do the same thing for b, then we're going to say negative 2ny bar plus 2mn x bar plus 2nb. Right? You guys see where I'm getting those? I'm ignoring the things that don't have the b and the m and creating a derivation of this equation relative to m, this one's for m, and relative to b. You set them equal to 0. You can simplify even more by dividing by 2n, because there's 2 n's everywhere in here, so let's make this even simpler. If you simplify these equations, you get negative xy plus m times the mean of x squared plus b times x mean equals 0. And for the b, negative y bar equals m x bar plus b equals 0. So this one is already there. We can keep going with this, but this one's already here. Negative y bar equals m times x bar plus b equals 0. So to get y equals mx plus b, what point is on this line? X bar, y bar. That's a point you know has to be on your equation for line of best fit if what you're trying to do is make sum of squared errors as close as possible to 0. You could divide both sides by the mean of x and keep going, but you can simplify this out. Negative y bar equals m times x bar plus b equals 0. All we did was algebraically simplify our equation for the sum of squared errors to get it equal to 0. So if you plug in x bar, y bar, you're going to get your best possible values of m and of b that will make sum of squared errors 0. Okay. I know that was a lot of writing on the board and a lot of x, y, this, m, this, da, da, da. But basically we said if sum of squared errors is taking the distance from each dot that is real to our prediction of where that dot should be, we assume that the x's are measured correctly. So we only need to find the vertical distance. That's why we look for the distance from y bar to, from y to y hat, because we have the x and there is a real y. We want to make the line that puts the prediction of y as close as possible to the actual value of y. So when you make the equation, when you spell it all out, then you have the distance from the dot to the predicted dot. To solve all of that out, you just write it out for every single dot. You can algebraically expand that, simplify it down. You're going to end up with the equation equal to y bar equals mx bar plus b. If you want that to be 0, then plugging in x bar, y bar will give you the best possible value of b that will make your equation as close as possible to all the dots. So you will minimize the sum of squared errors by having the point x bar, y bar on your line. And we know that conceptually that makes sense because we're trying to predict how these move together and describe where people would fall on these values. We're going to have the mean of each of those values on the line because we're making guesses about where people fall. We're going to change our guesses for y with respect to x based on the relationship. We can describe the relationship by trying to get a line that puts our predicted points as close as possible to the real points. And the best way to do that is going to have an equation y equals mx plus b that has the point x bar, y bar on the line. That actually took us all the way up to 3 o'clock. It's 3 o'clock, so I'm not going to keep you past then. There's a lot of faces that now look upset. I'm hoping that's from something else. We could do this all day. It's really fun. We could expand every single equation and simplify them all down. And you end up with this mess that looks ridiculous. But as you cancel out constants, you can see it distill and show you why you'd expect to see each of the things that we say are supposed to be there. But in a lot of stat classes, they'll just say, this point's going to be on the line, and it crosses the origin, and you plug them in, and that describes the relationship moving on. I want you guys to know how it describes it, why it's there. It's now 3:01, so I'm done. I will see you on Friday. I have put the participation self-assessment on ELC. Sorry, that's my old university's platform. On Blackboard, your Blackboard Learn page. Please take that. You can take it up through the end of class on Friday. I'll remind you again on Friday. But we're at the end of the semester, and participation is a big portion of your grade for this class. If we disagree, I'll go with mine, but I'd like to see you guys do your own self-assessments of your participation. So that's on Blackboard for you. Please fill that out. I will see you on Friday. Okay, that's it. Thank you, guys. Bye.
Thank you.
Thank you, Professor.
Thank you. Dr. Kelly?
Yeah.
I have a quick question.
Is our final exam are we